Okay, now we're going to talk about something we've come across in a specific format already, but we'll address it more generally here, the idea of what are called factorial moments. So when we were calculating the variance of the geometric distribution, we saw this, and it was a convenient way to calculate the variance and the second moment. And that turns out to be the case often, or in a few cases in discrete, especially when we're talking about discrete random variables. And so we'll introduce the formal idea here in general. So for random variable x, let's define mu sub k is going to be defined as the expectation of x to the power k. This is called the kth moment of x. Okay, so it's called the kth moment of x. And then we're going to define nu sub k to be defined as expectation of x falling factorial k. This is called the kth factorial moment of x. So for an example, expectation of x equals first moment is also equal to the first factorial moment because x falling factorial 1 is just x. But the variance of x we can express as, we know, the second moment minus the first moment squared, right? Remember, we're just writing different notation, right? The second moment is expectation of x squared minus the first moment expectation of x quantity squared. That's the computing formula for variance. And as it turns out, we can express the second moment. So look at it up here, expectation of x squared, second moment, and no, second moment, second factorial moment, expectation of x falling factorial 2, which is expectation of x times x minus 1. So it's the expectation of x squared minus the expectation of x. So the second factorial moment is equal to the second moment minus the first moment. So the second moment is equal to I'm flipping it around, second moment equals second factorial moment plus first moment. So this gives us second factorial moment plus first moment minus first moment squared. But then, since this is in terms of the first moment, and we know that the first factorial moment and the first moment are the same, we can replace the mu ones with new ones, and we get this expression. Okay. So in general, how do we how can we perhaps understand the way that we calculate factorial moments? Let's let A1 up through AN be n events. And let's let X some of the indicators of the events be the number of events that occur. So we're going to define a random variable. Just so IAAJ, just for clarity, this is the indicator of this event. We define it to be 1 or 0. 1 if AJ occurs, 0 otherwise. So X is the sum of these indicators, which are 1 if something occurs. So it's just the number of events that occurred. And in this notation, nu1, which is the expectation of the first factorial moment of X. Well, this is a sum of expectation of Bernoulli random variables. Right? These are Bernoulli random variables. Their mean is just their probability of occurring, which is probability of AJ for each J. This is what we defined as S1 when we were deriving our formula for the inclusion-exclusion formula. Okay. How about the number of pairs of events to occur? The number of pairs of events right, is the sum of pairs of the indicator of AIAJ. Indicator. Intersect AJ. Okay. The number of pairs of events to occur is, well, whichever events occur, then you have to take pairs, right? So it's choose a pair, it's X choose 2. X choose 2 is X times X minus 1 over 2. Right? So then in this case, then nu2, which is expectation of X times X minus 1, is equal to 2 factorial times S2, where S2 is the sum over pairs of probability of AI intersect AJ. And so on and so forth. If we define SK as the sum over sets of size K, probability of this intersection of all K-fold intersections of events, then nu sub K is K factorial times S sub SK. So that's how we think of, and that's how we can compute factorial moments. And that's a little bit of context for where they come into play. And also, as we saw in the case of the geometric distribution, there's just times where it's easier to calculate a factorial moment for whatever reason than for the moment. But we can, as we saw up here, relate moments to factorial moments and vice versa. And sometimes that's a helpful technique.